Okay. Michael Faraday has his own law. It's called Faraday's Law. It shows you the relationship between amps used and the quantity of product formed or reactant consumed during an electrochemical process. Okay? So the amount of substance produced or consumed at an electrode is directly related to the coulombs of charge flowing through an electrolytic cell. The amp is the SI unit for electrical current. The symbol is a capital A. And an amp is equal to 1 coulomb of electrons flowing through a certain point in a second. Okay, if you take a look at the bottom of this page, they give you that constant, and we will be using this constant. Can I move the page down? Okay, so we will be using this here when we take a look at a problem, and we'll probably be using this. Okay, so let's turn to the next page. Let's go straight to a practice problem. We just did definitions, Jules. Okay, sorry. Okay, you're fine. Okay, let's take a look here. We've got figure 7.5 depicts a cell used in the production of aluminum metal from bauxite ore. What mass of aluminum is produced if we have 15 amps going through molten bauxite for 24 hours? Okay, so what we're going to do is we're going to take the 24 hours and we're going to convert hours to minutes, minutes to seconds, and then we will use the conversion of 15 coulombs per second once we get there. Okay, so there are 60 minutes in an hour, 60 seconds in a minute, and then use this 15 coulombs per second. Then we can also use the other constant on the previous page, which was 96,500 coulombs per mole of electrons. Okay, and then now that I've got moles of electrons, since we're using aluminum, if you look at the SRP table at the half reaction for aluminum, okay, it says that aluminum metal will form an aluminum ion and 3 electrons, okay? You're going to use these electrons in this equation. So for every mole of aluminum, there will be 3 moles of electrons, okay? So over here, you will say that you have 3 moles of electrons for every 1 mole of aluminum, and then you can convert aluminum into grams. I have not seen something on the AP exam like this. Just giving you a heads up. This is going to give you 121 grams. Okay. It's just a lengthy unit canceling problem. I'm going to be more concerned with the equation on the next page for you. Okay. So let's go to the next page. You're good, Jules? Yes. Okay, let's come over here. Let's talk about free energy and electrochemistry. So free energy of a redox reaction actually pushes electrons through a circuit. So if you're not at equilibrium, then Gibbs free energy gives you the electrical energy to do work. And let's take a look. Let's come down here. Okay. Standard free energy is equal to the negative N. This N right here is moles of electrons. Okay. This F is Faraday's constant. And then E is just the electrochemical or electrical potential difference. And you can turn the page. So sometimes there's going to be some energy that's wasted as heat. Can I turn the page? Okay. So just because it's spontaneous doesn't mean that it's going to be like 100% efficient. So some energy is going to be lost as heat. And so some of your experimental values might be different than stuff like theoretical values, but generally speaking, spontaneous processes will always result in a positive E and a negative G. You should absolutely know that. This right here should be second nature to you. You should automatically know that if you see a negative G, it's spontaneous, and that if you see a positive E, it's spontaneous. And then take a look at the next page. Let's go over here. This figure is relating everything to each other. So K and your voltage for a cell, and then the spontaneity or Gibbs free energy. So thermodynamically favorable processes have a positive E, a negative G, and then when you substitute it into the equation, negative G's and or positive E values always result in K's that exceed 1. I would probably know this if I were you. And then the greater the delta G or E, the larger the K. I would also know this. And then if you reverse the signs, K will be less than 1. That's just... Take a look at the next page. They outline it all for you. I would know this table. This just summarizes it all. Delta G, K, and E, they do not impact the kinetics of a reaction. The magnitude of the activation energy and the rate constant will affect the rate. These are independent of the thermodynamics and what's going on in terms of the electrochemistry and the equilibrium position. Only temperature will influence thermodynamics, electrochemistry, kinetics, and the equilibrium position. So that's it. That's the end. We're done. Okay.